So this is one of the flipped content sections. This one I'm going to cover excimers and exciplexes, as well as the basic principles behind how lasers work. So excimers and exciplexes are probably words you've never kind of come across before, but they're kind of both properties of having an excited state. So if I look at an excimer quite literally means an excited state dimer. So in my ground state, I have two separate, completely unassociated molecules. However, when I excite one of those molecules, there is a lower energy form, which is when I start to get that excited state shared across two molecules. So one excited state gets shared between two molecules, and overall I end up with a lower energy state. So here I've got an example of it happening with pyrene. We end up with an interaction where the two pi stacks end up interacting quite close, about 3.5 angstroms. And we can see that this excimer has a lower energy transition than I get from the excited state monomer. In the ground state, there is no interaction between the two pyrene molecules. So on this next slide, I've kind of got, if we go back to our kind of, just think about our binding between two atoms, and we have our energy level diagram, and we see a potential well when I end up with binding. We can see here I end up with that potential well in the excited state, whereas what would normally be my anti-bonding region, where I end up with it just being essentially a degrading potential, that's what I have in my ground state. So in this case, if I'm looking at my energy level diagram, I can see my two non-interacting molecules are given to me in the pink line. If I excite straight up, I end up on this kind of flat portion towards the right hand side, where this is where I've got this excited state chromophore and a non-interacting other chromophore in its ground state. But if those two come together, I can end up in this lower energy region. So excimers are usually very, very easy to spot because I can see a very characteristic band in the spectra. And this is what I've tried to show on the left-hand side of this image. So it's kind of turned at 90 degrees to how it normally is. So my wavelength is kind of going upwards, but it's to kind of match what's going on in this energy level diagram. So if I think about what's going on, for my monomer, I see these kind of reasonably sharp transitions. They're reasonably sharp because the ground and the excited state structure are quite similar. And these are the transitions I've got over on the far right-hand side. So from the vibrationally relaxed excited state monomer down to different vibrational levels in the ground state, and we see these kind of reasonably sharp things. But then we can see at lower energy, at higher wavelength, I see a broad Gaussian, completely symmetric band, which is actually my excimer band. This excimer band has lifetimes in the orders of nanoseconds, and it's something that we only get to see really at high concentration. I need to have a high concentration because I need to have enough concentration that an excited state chromophore will meet a ground state chromophore. If I have very low concentrations, the probability of this happening is very, very low. As I increase the concentration of my dye, then I increase the chances of this happening. So a very classic way of spotting whether we have excimer emission is to change the concentration of my sample. And if I see this broad Gaussian band growing in at lower energy, higher wavelength, as I increase my concentration, I almost certainly have an excimer and nothing else. An exciplex is slightly different from an excimer, but again, it's derived from the fact that we are going to have an excited state on my dye molecule. Here I've labelled 2 molecules, one D for donor and one A for acceptor. And an exciplex is essentially a charge transfer complex. I have an excited state charge transfer complex, which is the origin of this name. I generate my excited state, and then I have a tendency that there will be some form of kind of rearrangement of the charge when my donor, my excited state donor, and my acceptor meet. Now, from my exciplex, what I usually see is emission from this kind of paired complex. However, exciplexes can go on to further react, and I can end up basically inserting a solvent between my donor and acceptor pair, and this is what we would call a solvent-separated radical ion pair, and this can go on and, again, just lose that excited state, return to the ground state, or I can take it to completion where I ultimately end up by having a dissociation and a charge transfer reaction happening. Exciplexes are really important in a lot of the current trends happening in photochemistry, particularly with light harvesting compounds, and a large amount of work is being done with trying to separate charges in this manner, because if we separate charges we can recombine them to get that energy back. So you'll notice that everything associated with this formation of the exciplex is at a higher energy than my ground state donor and acceptor. So this is a method of me storing energy. Therefore, I can keep solar power for when it's nighttime. If I actually look at the energy level of the energy level diagram of what's going on in an exciplex, I can see that it's more complicated than what goes on in an excimer. I have my ground state donor and acceptor, and if I absorb a photon of light, I'm going to generate an excited state donor acceptor system. Now, the formation of the exciplex is lower in energy. However, it's going to take a little bit of energy for me to form the kind of separated charge transfer complex. But we can do that overall by other kind of methods, whether that is a little bit of heat that we can collect from the solar power, or whether that is a second photon which helps to kick this system along. But my exciplex is stable. Again, it's fairly long-lived, nanoseconds to microseconds even in some cases. And so I have plenty of time to kind of do further chemistry, which isn't going to be stable for very short periods, nanoseconds and picoseconds, which although are quite long-lived in terms of photochemistry, aren't good enough to light my house at night. But it gives me plenty of time to be able to form this charge-separated complex. Now, if we think about what's going on in terms of this process, an organic solvent is a far better environment for actual exciplex formation than it is for charge transfer formation. So if I want to have an exciplex and store that exciplex, organic solvents are the way to go. Exciplexes themselves show very similar properties to excimers. I again end up with a broad Gaussian band at lower energy, higher wavelength than I do from my regular emission spectra of my sample. In this case, though, it depends on the concentrations of two factors. If I remove an acceptor, I don't see this band, then it's almost certainly exciplex formation. However, if I still see it, it's likely to be excimer formation instead. So again, I've included one of these Twitter questions. This is kind of a proper problem-based kind of example of what happens in the lab. So I have here a very short-lived blue emission in the solution phase, which shows a very long-lived violet emission in the solid phase. So I'm posing you the question here to combine what you've done, what you've learnt, not just in this flipped video, but in the lectures. Can we identify the types of emission that we have in this sample? I'll give you a couple of hints in terms of this, think about the different pathways for deactivation of my excited state and how those change between the solution and the solid phase. So a slight change of topic now. We're now going to start to talk about the processes that go into kind of the basic principles of a laser. But to start that, I have to understand the difference between spontaneous and stimulated emission. Spontaneous emission is the type of emission I've been talking about all the way through this lecture course. It is a first order process which, just like radioactive decay, essentially is a random decay from an excited state. There is a certain probability at any given time that a photon will, or an excited state will decay to release a photon. That probability does not change. All that changes is the number of excited states I have. And so I see this exponential decay from the concentration of the excited state. From looking at what we've learned from things like the energy gap law, I know that as I increase the gap between my ground and my excited state, I increase the favourability of radiative transfer from the excited state, rather. So if I have my excited state here, what happens is just randomly, spontaneously, I will drop from that excited state and I will emit a photon. It is entirely based on statistics. The second type of emission I can have from an excited state ultimately leads to the same transmission. But in this case, I have a photon coming in as well. So in this case, I call it stimulated emission. I have an excited state and I have a photon of exactly the same energy as the emission from that excited state. And what happens is I will essentially tickle that excited state. That was the word that I was taught when I was studying this, which will cause the excited state to lose its energy, and I will have essentially two photons leaving, or I've shown it here by a more intense electromagnetic wave. The case of stimulated emission doesn't rely on statistics. It relies on the intensity of the incoming light. The stimulated emission will always have a photon of exactly the same energy. It will always be coherent. In other words, it will always be going in the same direction. And it will always be in phase. So I don't end up with any cancelling effects. So I can apply a bit of chemistry to this, and all I've done is I've looked at the probability of these processes happening, and I've come up with this equation here, which relates the concentration of my excited state and my ground state to the number of excited states, the rate of natural spontaneous emission, or fluorescence as I call it, the rate of formation of my excited state, which is my K-abs, and my rate of stimulated emission, which is my KSE here. So stimulated emission is a process that actually competes with stimulated absorption. That photon coming in, if it meets a ground state, will excite up. If it meets an excited state, it will stimulate a process where it comes down. So how does this help me with my lasers? One photon coming in, two photons coming out. Well, that's the start of it. If I think about this in kind of a bulk situation, I can have my vast quantity, and I've shown about 9 or 10 here, of chromophores. They have their occupied highest they have their occupied highest electronic orbital, and they have their lowest unoccupied molecular orbital as well. And what happens, light comes along, I excite some of my molecules into their excited state. So now, what happens? Well, more light comes along. I have some which excite into their excited state, but you'll notice others drop down into their ground state. This is the process of one, stimulated absorption, forming the excited state, but stimulated emission, forming the ground state. So this stimulated emission, the fact that my light is always going to be coherent, in phase, monochromatic, is what the basis of my laser is. If I go from an example where I've got 9 or 10 molecules to an example where I have essentially billions and billions and billions of molecules, I can end up with a system where I have the lasing action taking place. So laser stands for light amplification by stimulated emission of radiation. I have a cavity here, which basically has my laser medium in it. We call this our gain medium. And I have mirrors at either end. The mirrors are separated by whole numbers of wavelengths of the light that I have. And I have a small gap. You can see this just at the right-hand side, a very, very small gap for the light to come out. So in this case, I am going to excite, and we excite our laser by any usually form of light, but heat, anything that will get me up to the excited state will work. Light is best, it's the easiest way to get there. And what happens is the first photon that basically matches the cavity, so it's going in the right direction, so it's running along the length of the cavity, and it's also kind of running, so its wavelength is kind of the right layout on the cavity to not interfere with itself. That will start to build. It will go from one photon, and then as we get that stimulated emission, others will join in. All coherent, all in phase. And that's the basis of how a laser works. But there's one important fact that I haven't kind of mentioned. Why don't most things laze in that case? If that's all I need, if all I need is a bit of stimulated emission, why don't most things laze? Well, the reason being is that actually I need a population inversion to make it happen. To make stimulated absorption not be the favoured process from stimulated emission, I need to make sure I've got more things in the excited state than I have in the ground state. This is incredibly rare. We know that excited states are far more uncommon than ground states. We know that, normally I'm working in a system where I have very few excited states and a large number of ground states. So I need to have something called a population inversion. So single state lasers, in other words, a case where I don't have a change of spin in my system, are not at all possible. So we have the basic principle of how lasers work, but things don't tend to laze. The reason being is we actually need a population inversion. To ensure that we have more stimulated emission than we have stimulated absorption, I need to make sure that I have more excited states than I have ground states. This isn't quite so simple as it sounds. In terms of I can never do this with a singlet state, because everything will just have the tendency to drop back down again before I get that population inversion. Therefore, I need to have what is called a metastable state in order to do this. And there's an easy way of achieving this. If I think about kind of my regular Jablonski diagram, I have my singlet state and I have that triplet state. Well, that triplet state is much longer lived. It has a different excitation wavelength than it does an absorption wavelength. There's no overlap of the spectra there. And so this is the way that I'm going to access my triplet, my kind of metastable population inversion state. So we know that we can't do that in any other way. I can't heat it above there. I can't get it any other way. If I try and heat it, I'll just still increase everything that's going on at low temperatures and I won't get that state. It has to be with a triplet. So by having a change of spin, my stimulated emission process is allowed to have an inverted state. But I also increase the proportion of things that occur by stimulated emission rather than spontaneous emission, because that triplet state, that change of spin state, has a very long lifetime. It needs that kind of help to decay. And so having that stimulated emission state is very, very useful. And so the basic principle of lasers is that by having either a 3-level laser, so that is a traditional kind of Jablonski singlet triplet thing, and having spontaneous emission from that triplet state, starting off the stimulated emission process, so one photon spontaneously emitting in the right direction and the right phase, that will lead to my stimulated emission that will all happen in that lasing category. And I can generate that because I'm not competing for my absorption and my emission at the same thing. I can also do this with the 4-level laser, which is essentially having, again, that kind of singlet, triplet level. But quite often lasers are actually based on my Excimers, which is why I've kind of linked these two things together. So very, very common lasers are Excimer lasers. I'm not going to go into kind of the actual engineering or physics of how a laser works, but these are the kind of basic photophysical processes of what goes on.